Welcome to Lesson 27, Indefinite Integrals and the Net Change Theorem. So we learned in the Fundamental Theorem of Calculus lesson that we can use antiderivatives to evaluate definite integrals. And so what we're going to do in this lesson is basically use that same integration notation without limits to just denote general antiderivatives. So that will keep everything consistent, that we're really using antiderivatives to do integration. So these are going to be called indefinite integrals. And this notation will look like this. We'll use the integral symbol, f of x dx. There just won't be any limits, no a's and b's. That will equal capital F of x. And that means that the derivative of capital F, f prime of x, is equal to the integrand, f of x. So in other words, big F is an antiderivative, right, of little f. And this integral of f of x dx without the a and the b is called the indefinite integral of f. So indefinite integral is the thing that we are defining here. So just notice that all we're really doing is giving a notation for a general antiderivative. So in these two examples here, we're basically just going to try to find the antiderivative of x squared or the antiderivative of 1 over 1 plus x squared. So those should be pretty straightforward. Remember, when we're doing a general antiderivative, we need the plus c to denote that we don't know what that constant could be. There is, in fact, a whole family of functions that are antiderivatives of x squared. And same with this one, it's an inverse tan, but we need that plus c to denote the general antiderivative. So even though the notation is the same, there is a big difference between definite and indefinite integrals. Right? So definite integrals, the ones we started with, right? These result in a number. The answer to a definite integral is a number, right? And that number equals the net signed area over the interval a to b, where when a and b are limits of integration. So it's a number that has a graphical interpretation, whereas an indefinite integral, like what we just did above, x cubed over 3 plus c, this result in a family of functions. And so we did that in lesson, I want to say 23, where we drew some members of a family of functions and talked about how that's what an antiderivative really is. Unless we have a specific initial condition, then it's a whole family of functions. So even though they look like they're the same, they are actually very different in the way in what they result in. So on this next page, there is a whole table of antiderivative facts. I won't go through all of these, but they're basically most of the things we talked about already in lesson 23, like factoring out a constant, sum and differences, integrating a constant, the power rule, how we deal with x to the n, how e to the x is its own derivative, 1 over x, of course, etc. So I'm not going to go through all these. You'll see, though, that this table does also include like antiderivatives of some trig functions and a couple of the antiderivatives of inverse trig functions, because we do end up using the inverse trig, particularly the inverse tan and the inverse sine. So that's how they ended up in this table. It's not a comprehensive list, but it's just kind of a place to start to help you think about going backwards. If you've already memorized the derivatives of things, then you don't really need to memorize antiderivatives. It's just going in reverse, right? So there's a couple problems here. This isn't new. You should be able to do these without any help from me. So why don't you go ahead and pause the video and give them a try. Okay. Pretty straightforward on the first one. We're just going to use our power rule on the 6x cubed. And then the antiderivative of secant squared is tangent. Don't forget your plus c. And to simplify. I think we did some of these, like number 2 in lesson 23. I'm going to go ahead and break up the sine squared into sine times sine. So then with one cosine on the top, I have a cosine over sine times a 1 over sine. Convert that to cotangent cosecant, which is the antiderivative of negative cosecant. And last but not least, I've been working on this since we've been doing derivatives. If you've got one monomial, one term in the denominator like this, don't try to do a product rule to take the derivative. I'm sorry, a quotient rule. And similarly, don't try to do anything too fancy with the antiderivative. Just divide everything by that t squared, simplify, and then do your antiderivative term by term.